Okay, this is carboxylic acids and their derivatives, slides 20 to 26. We're now going to start talking about one of the derivatives of carboxylic acids called acid chlorides. And acid chlorides, if you recall, are one of the most reactive carbonyls of all, right? If you remember the trend for an acid chloride, it's a withdrawing group, the electron withdrawing group. That makes the carbon extremely electropositive, right? It's way more reactive for nucleophiles to attack than, say, an aldehyde, which is neither electron donating nor electron withdrawing, which is more reactive than a ketone, which has an extra electron donating group by induction, which is more reactive than, say, a carboxylic acid or an ester, which have electron donating groups that are actually donating by resonance. So the electron withdrawing nature of the halogen actually make the carbon way more electropositive. So what can we do with them? Well, I want you to recall that this reactivity, it's so reactive that we don't often need a nucleophile to be strong, okay? This means that the nucleophile doesn't need to have a formal negative charge. Doesn't need to have a formal negative charge. So because of its enhanced reactivity, it may as well be an absolute positive. This is why we make acid chlorides fresh. We don't buy them very often because by the time they get to us in a bottle, they've already reacted with even the moisture in the air. And so they tend not to be very good when you get them. And because they're so reactive and they generate gases, we don't like to ship them via plane. So they tend to be truck only and expensive. So the best thing to do, which is what I showed you last time, is just buy a cheap, very stable carboxylic acid and then convert it to the acid chloride when you're ready. For this reaction, we're going to use water as our nucleophile. So water is being driven on, the chlorine is being driven off. These are the easiest 1,2 additions. We don't even need an acid catalyst. It goes in and up. We do down and out. And we work it up under mildly basic conditions to remove the extra proton and get us to the carboxylic acid. I'd say acid chlorides are even easier for the 1,2 addition. In, up, down, out. Driving the water on, driving the Cl off. And it looks like an exchange. Okay, moving on. How about if we reacted an acid chloride with an alcohol? Again, you don't need the alcohol to be charged. You don't need the carbonyl to be charged. You know what? I'll make this ethanol just to make it something very specific. We're going to do in, up. We're driving the alcohol on. We're driving the chlorine off. We're going to get an exchange in and up. Driving the chlorine off, driving the alcohol on, good reminder. Now we can do down and out. down and out with the better leaving group. I've exchanged now the chlorine for the alcohol, and now all that's left is to work it up. Oops. Work up under some mildly basic conditions, removing that extra proton, and I end with an ester. There you go. Again, look from start to finish. We've exchanged the chlorine for another group. Now, as an aside, how do I know not to keep going? Well, I know not to keep going for two reasons. One, esters are not super reactive. So if I had another alcohol molecule, right? The alcohol is partially negative, the carbonyl is partially positive. You typically would need an acid catalyst to keep things going. How do I know not to keep going? The other thing is that if you remember, having a carbon with two oxygens off of it is unstable because of down and out. Think about adding more oxygens off them. It's going to, even if I did add another in up, I would have 3 oxygens around that carbon. The O- would certainly come back down and kick out, ultimately giving us the ester at the end of the day. It's the most stable system. Try it out yourself, right? Basically, you would just end up with O-, and this would largely be disfavored. So even if another addition occurred, you would end up with this carbon and 3 oxygens around it, right? It's like an acetal with another oxygen. I mean, definitively, it's just going to collapse back to the ester. So it's just an unstable intermediate that even if it happened, it wouldn't stay put. It's not stable. Okay, what about an acid chloride and an amine? These two are very easy to write out from a 1,2 addition standpoint. And I could have an ethylamine. It doesn't really matter what kind of amine I have. I wrote ammonia, but I could have written a different amine, maybe an ethylamine or a methylamine, a dimethylamine. The amine is already basic, nucleophilic, so this is not a problem. Very, very generous with its lone pair and willing to react. You can remind yourself that you're driving the nitrogen on, you're driving the chlorine off. But because we don't even have to do acid-base catalysis here, we can do straight out in, up, down, out. Down, out. And we're there. All we have to do is work it up. Work it up to take off the extra proton. And you formed the amide, or the amide, the amide. And there you go, in, up, down, out. Easiest when you're dealing with an acid chloride, much easier, right? It's like an even exchange, in, up, down, out. Okay, here's a quote unquote new one, but this one is not terribly difficult. If you look at the reagent itself, it's a very specific reagent. Let's draw it out. It's aluminum. Ooh, I see aluminum. Remember, aluminum has 3 valence electrons. That means its formal charge is 0 when it has 3 bonds. Look at what the bonds are. OR, OR, OR. Wait a minute, it has an extra. Ooh, the extra is the hydride. The aluminum is therefore negative, and the counter ion is lithium. So this is very similar to when we had lithium, aluminum, hydride, with 4 hydrogens around the aluminum. This reagent is 4 equivalents of H-, right? So it's kind of like adding 1 molecule of that is like saying you're adding 4 equivalents of H-, like 4 H- molecules. This reagent very specifically has strong aluminum oxygen bonds and only has 1 available hydrogen to give. So it's controlling the amount. It's only got 1 equivalent of H-. And so it's a very controlled reaction. And it also is controlled because of the way that the aluminum is offered. So let's write this out. Basically, you can think about it from a in, up, down, out standpoint again. Let's draw this out. In, up, there's an H-, that's going to be driven on. In and up. We're driving the hydrogen on. We're driving the chlorine off. Down and out. Now, even much more than this, the oxygen is actually going to interact. So you can sort of think about this as a if you look at like the next one, what I'm going to be doing is we're going to be adding lithium aluminum hydride, the 4 equivalency. What the other thing that I want to mention here that'll help you in understanding how it doesn't continue is that acid chlorides are way more reactive than aldehydes. And because you're controlling the equivalency here, and there's also possibility of having the oxygen react in a Lewis acid way with the aluminum that's once the aluminum kicks out the H-, it's back to its normal bond trend, but it thinks it wants to have, it thinks it still wants to have an octet. So what in reality, what's possibly happening is that at this part, before this happens, this sits here until workup. And I'll show you a little bit more about this mechanism as we move along, as we move forward, because there's going to be another reaction called dibal that has a very similar intermediate. But for now, let's just treat this as a 1 equivalency where the acid chloride is just so much more reactive than the aldehyde that even though you've just got this 1 equivalent, it's going to keep reacting with the starting material. And so ultimately, after you've burned out all of your H-, you'll end at the aldehyde. Okay, so we'll just treat this as a typical in, up, down, out. And you'll see that this is okay to just treat it as an in, up, down, out. Why? Because the acid chloride is so much more reactive than the aldehyde. So even after you get to the aldehyde, aldehydes are susceptible to H-, but the acid chloride is so much more susceptible to the next equivalent of H-. So it just continues on as long as you do a 1-to-1 ratio. If I use my typical lithium aluminum hydride with 4 equivalents of H-, well, now you can imagine that you can't stop the train at the aldehyde. Right? Effectively, you've got excess H-. And we do in, up. And then we do down and out. Lots of flashcards for this chapter, but none of them have a crazy mechanism if you are seeing the trend. Okay, so we did the first one. Aldehydes are susceptible to lithium aluminum hydride. We saw that in the aldehyde chapter. So we just keep going because the reagent itself already has 4 equivalents. So we're going to do in, up again. In and up. We've added 2 hydrogens. I'm now stuck. The down out cannot happen anymore because I've got hydrogen, hydrogen, carbon, so I'm done. Work it up under acidic conditions. Acid-base workup to protonate my alcohol. So carbon 1, carbon 2, carbon 1, carbon 2. So you go all the way to the alcohol. As opposed to the previous slide where we stopped at the aldehyde. We only did it once, and that's because of the nature of the reagent and the fact that the starting material is so much more reactive than the product you're forming. Here, you just dump lithium aluminum hydride is like 4 equivalents of H-, so you're just dumping it in and it just keeps reacting until you finally get all the way reduced down to the alcohol. All right. The last one I have for acid chlorides is with a Grignard reagent. And we actually already did this one. When I first introduced the Grignard reagent to you, we actually did an acid chloride with a Grignard. I could give you ethyl magnesium bromide, for instance. You're going to drive the Grignard on. You're going to drive off the chlorine. The carbon is minus. It goes in and up. Chlorine is going to come off. We've just driven the ethyl group on. And now we can do down and out. These reactions are not reversible because I'm driving on a carbon, just like the last one. The last 2 were not reversible either because I was driving on a hydrogen. Now the question is, do I keep going? What do you think? Are ketones reactive with Grignards? They are. So because a Grignard is reactive with a ketone, yes, it is more reactive with an acid chloride, but you're going to start getting mixtures. Grignards are really strong nucleophiles, so you're going to get mixtures. So if people were running these reactions, you just kind of keep going. Just expect that it's not going to stop, or not efficiently stop, at the ketone. So we're going to do another in up. You almost have to put yourself back in that ketone chapter and say, are ketones interactive with Grignards? Yes, they are. In and up. And you keep going until you can't go no more. Now I have 2 ethyls that I've put on, and I'm done. I can't come down and out anymore because I have carbon, carbon, carbon. So I work it up under acidic conditions and get the alcohol for this case. And that's it. That's a review reaction. We did this one in a previous chapter. So where are we at? Well, we have now covered from the acid chloride. We saw already that we could take an acid chloride with the carboxylic acid. I showed you this when we were talking about carboxylic acids, and make an anhydride. We now know that acid chlorides with water, right, go back to the carboxylic acid. Acid chlorides with alcohols give us the ester. Acid chlorides with amines take us to the amide. Acid chlorides with the special 1 equivalent hydride source stops at the aldehyde. Acid chlorides with the 4 equivalent hydride source go all the way to the alcohol. And that pretty much covers it. We've now got a lot of arrows here. Not too many left.